Good morning, everyone. So I hope you enjoyed the poster session yesterday. As I mentioned also yesterday, tomorrow is going to be the day that we're all going to be locked in pretty much here. And we'll postpone our hike to Thursday when the weather is supposed to be better. So we may get some snow tomorrow. Let's enjoy it. But we still have today. Gerhard Rempe is going to, like yesterday, begin the first lecture of the day. So please.
It's a pleasure for me to be back. Good morning, everyone. So this is part 2 of our rather long journey of unknown territory, polyatomic molecules. So you have seen the title yesterday, and only one word has changed. So yesterday we had slow polyatomic molecules. Now we will talk about how to cool them, how to cold polyatomic molecules. And I said yesterday, slowing or slow, that refers to the velocity. Velocities are small, when we talk about slow, it's velocities are fast, about a meter per second or whatever, then they're not slow. But temperature temperatures, a little bit about phase wave density sometimes. And this is what I will talk about today. Slowing can be done with conservative forces. I mean, just take this, it's going up. Okay, when it's up there, it's slow. But purely conservative potential, you wouldn't call it cooling. No? But now we talk about cooling, and cooling requires dissipation. Okay. So we need to implement some dissipative mechanism. From velocity dependent force. Velocity dependent force can cool. If there was a heat depending on sign. If the force is positive, it heats. If it's negative, it cools. Okay. So let's talk about the cooling strategies or basically. And I will tell you during the next 60 minutes or so, I will tell you about 2 different cooling strategies. The one acceleration or deceleration strategy, which has to come with one of the cooling. Anyway, so this is more or less the content of today's talk. The cooling we will have is a little bit shown here. What we have is, of course, molecules. Their molecules are flying around, and they will be addressed by just one laser. Just one laser beam. And there's radio frequency fields. And this radio frequency field I will specify a little bit further on. So the first question is it difficult to cool molecules? Especially polyatomic molecules. I mean, when we started research, as I said yesterday, 10, 20 years ago, so there were no cooling experiments. Now there are cooling experiments with many kinds of molecules. They're basically doing radiation pressure. This is something we cannot do, and I will tell you why. But let's address the simple question: why is molecule cooling so difficult, or maybe not? I think once you have treated it, it's more difficult. But the question is, why has it been considered to be difficult? This is a comparison of the energy level diagram of rubidium atoms. You also use it by that. And fluoromethane. Okay. And typically rubidium has a ground state manifold. These are the 2 ground states of hyperfine splitting, and then as a function of the magnetic field, there's Zeeman splitting, and so on. This is the first excited state here, or maybe the second excited state, 5p3.5, maybe the 1 again, hyperfine splitting, and again the Zeeman splitting. Okay, this is known to everyone who have standards, nothing new. This is fluoromethane. It looks very, very similar. It's a J equal 1. I mean, this is well, I'm not talking about the ground state here. J equal 0 is missing. J equal 1, J equal 2, J equal 3, and so on. K equal 1, and this is maybe an excited state, and it looks very, very similar. I mean, there's hardly any difference between the molecular energy levels and the function of the electric field now, because molecules, as I said yesterday, the molecules do not react to magnetic field, or hardly react to magnetic fields. For these kind of molecules, there is closed shells, so there's no spin, no angular momentum of the closed shells. There's maybe a little bit of angular momentum of magnetic moment from the nucleus. This is very small, and it's weaker under the carpet is small. So as a function of the electric fields, it's very similar as obedient as a function of magnetic field. So why don't we just transfer the techniques that we have for the alkali atoms to the molecules? It's pretty straightforward. I mean, why can we not just drive a transition here and make, let's say, radiation pressure cooling or something like we do it for the airless and implement it very similarly to molecules? Why is that? I mean, if you look at this, it looks so simple. Why doesn't it work? So, a question to you. This is the answer. Nobody gave me an answer. So this is the answer. In rubidium, it's a very fast transition. It's an optical transition, optical wavelengths. It's very, very fast. Typically, the lifetime of the excited state is maybe 10 nanoseconds. So not all of that. Doesn't matter, it's a factor of 2 or 3 more or less. It's of the order of 10 nanoseconds. So that's fast. But once you excite it, immediately decays and radiation pressure works like that. Radiation pressure fully works like that. You can cycle really fast. I will give you some numbers in one of the next slides. In the molecules, this would correspond to vibrational transition. From the vibrational ground state to the first excited vibrational state. If you go to the electronically excited state, then there are quantum factors in some other states. You lose these molecules because quantum factors are pretty, well, let's call it random. It's not really random. Of course, it counts with the molecular structure. But it's hard to control. There are certain kind of molecules where these quantum factors are kind of diagonal. But typically, this is not the case. In general, this is not the case. But in particular, not for these kind of molecules that we are talking about. So when we do an excitation, many things can happen. It can decay down to some other state which you can't control, or it can even dissociate. And this would be reversed because it would lose the molecule. So we are dealing with a vibrational transition from the vibrational ground state to the first excited vibrational state. This is an infrared transition. And it's very slow, typically of the order of 100 milliseconds, which is rather slow. I mean, it's many, many orders. 10 nanoseconds to 100 milliseconds. 7 orders of magnitude slower. So radiation pressure would be work 7 orders of magnitude slower for molecules than for our atoms. Okay. Let's give you a little bit of the numbers. So the recoil velocity, for example, for an optical transition is, let's say, depends on the mass of the molecule, depends on the mass of the atom, depends on the wavelength, and so on. But typically, it's, let's say, millimeter per second, centimeter per second. But then order of magnitude, that's typical recoil velocity. What do we mean by recoil velocity? Well, you absorb a photon, and that imparts energy due to energy momentum conservation. The photon disappears, and the momentum of the photon is taken by the molecule or the atom. And typically, this is millimeter per second. So in order to slow down the molecule or the atom from 100 meters per second or so with photons, with recoils of millimeter per second, you might need 10 to 5 photons. 10 to 5 photons, 100,000 photons. This can be done fast for atoms, but for molecules, it's kind of slow. So this number multiplied with 100 million is 10,000 seconds. The cooling of the molecule, radiation pressure, just taking the analog of the radiation pressure cooling from atoms, the analog would take 10,000 seconds, which is 3 hours. Oh my goodness. You need to have these molecules available for 3 hours. And you can do 1 measurement per day, maybe 2 measurements per day. Let's use more to go home. 2 measurements, I don't know. I mean, this is just incredible. So in principle, it works, yes, but in practice, it's not a viable solution. So this is why we decided some years ago, many years ago, actually 10 years ago, or maybe before, to just put the laser cooling history of atoms upside down for molecules. So for atoms, for example, you do first the cooling. The atoms come out of the oven, they're evaporated. They are somewhere in the background gas. And you do the cooling first because it's a fast transition, 10 nanosecond lifetime. And then once they're cold and slow, you can trap them in a shallow trap, like a magnetic trap, typically it's a millikelvin depth, or an optical dipole trap, which has a millikelvin depth or so. So for atoms, this is a standard scenario. Also for the laser cooling of the molecules with the diagonal quantum factors, this is a standard scenario. You have a very short lifetime, so you can do cooling first on a thermal ensemble of atoms and molecules. So you can do the cooling first and then you trap. In our case, with the molecules, polyatomic molecules, this is gigantic dipole moments. We just make it the other way around. We trap first, as I showed you yesterday. We trap the low velocity tail basically, 10 meters per second, 20 meters per second, something like this. Depending on the dipole moment, depending on the electric fields that we apply to the trap. So we have the deep trap, Kelvin or 10 Kelvin deep trap. So we can trap, and then we have lifetimes of minutes, seconds, minutes, whatever. And then we can do the cooling, even on a slow transition. But of course, you realize that if the cooling takes 3 hours, you wouldn't need to trap the atoms. And so we would need to trap the molecules for 3 hours. We can't do that. We haven't achieved that. So radiation pressure is not working anymore. But at least we can trap and then think about the cooling mechanism inside the trap. Okay, you got the general idea? Put just the laser cooling history from atoms upside down for the molecules. First trapping, then cooling. Because then we have these atoms, so we have the molecules available for seconds and minutes. So we need to implement a cooling mechanism. Takes place in a scale short compared to minutes. And this is a cooling scheme. The physical cooling scheme is a combination of a conservative electric of deceleration in a conservative electrostatic electric field gradient and an optical function. So let me explain to you how this is supposed to work. So this is a plot of the energy of the molecule and the function of position. And let's assume that this is the trap, this is the trap center, and then there are these walls. The boundaries, if you remember the kind of traps that I showed yesterday, it's kind of a steep increase of the energy of this particular rotational state as a function of position. No? It's just a schematic, of course, it's not a kinkier thing, but the trap center is kind of flat. That's what I tried to explain yesterday for spectroscopy and so on. So this is flat, and then there are these steep walls. And the steep walls on the deep there depend on the orientation of the dipole. The speed or the dipole moment times the electric field. And depends on the orientation of the dipole moment, like this one or like this one, how steep this actually is. Okay, and of course, this happens on one side of the trap, and this happens on the other side of the trap, which is outside the picture here, and it happens in all directions because it's a three-dimensional trap. Okay, so now this is a molecule, and it moves around. So of course, what can it do? It can climb the wall, it falls back down, and it's trapped. So it cannot escape the trap because it's trapped. So what do we do now? We shine in a radio frequency field, let's say of this value. This is just a splitting between the energy levels of a dipole, of the molecular dipole, aligned differently with respect to the electric field. So depending on the electric field, we shine in a radio frequency transition or microwave transition, depending on the strength of the field. And so we can drive a certain transition between these states at a certain amplitude. By changing the radio frequency, we can adjust the position where this transition can happen. So now what happens is if the molecule goes up, it sees the radio frequency, is split down into a state which does not have such a large dark field. And overall, it climbs a potential barrier which is large, and it falls down a potential barrier which is small. And the difference of these two is taken away from the kinetic energy. Okay, so it loses kinetic energy when it climbs the wall, and it gains kinetic energy when it falls back, but the gaining kinetic energy is small compared to the loss in kinetic energy that happened before. So it's very simple. It's a Stillitude effect, which is kind of well known from atomic physics, but now it depends on the molecules here. Yeah.
Is there no energy funded by your pump? Are you pumping?
This is the radio frequency. What do you mean, a recoil from the radio frequency? Oh, it's very small. Okay. Radio frequency. Okay. The momentum of a photon is h by k, or h over lambda. But this is a radio frequency, so the number is large, which means the momentum is very, very small. I mean, please remember, the optical momentum was millimeter per second. The recoil velocity due to an optical photon was millimeter or centimeter per second. And this is for 1 micrometer radiation, optical, half micrometer. This is radio frequency, maybe gigahertz. Okay, but now what happens is, what you can see is the molecule is in a different state. The molecule is in a different state. And if you want to repeat the cycle and send it back to the initial value at least, we have to think about a closed cycle scheme. Like a refrigerator line. Refrigerator cools the beer. We cool molecules, which is very similar. We need a cycling scenario. So how do we cycle back? So we cycle back, and please also remember, it's purely conservative. It holds up a hill, it falls down a hill. Purely conservative. There's nothing to do so far. So what we do is we excite the molecules to the first excited vibrational state, very much as I had in the previous slide. It populates the state, and it falls back. Very good selection rules, either to this state, and then nothing has changed, or to that state. And I tell you how we eliminate all the other states. One of the next slides. So it falls back, emits spontaneously a photon, which carries away entropy, because it's emitted into a random direction. And that brings the molecule back to the initial state. And we can repeat the cycle. Okay, we can repeat the cycle. Of course, what happens is the molecule has much less kinetic energy, so it will not reach this position anymore. By the way, it has lost a lot of kinetic energy, because please remember this here is of the order of a Kelvin or maybe several Kelvin trap depths. So this is maybe half the trap depth. So the molecule lost something like a Kelvin of energy. Huge amount. So it will not come back to this position. That's what I'm trying to say. So it moves up a little bit, comes back down. So we cannot repeat the cycle in the way we want. So we change the radio frequency, move it down, and repeat. Okay, so that moves this way. And so by sweeping down the radio frequency, adiabatically cool, or well, adiabatically is maybe the wrong word, because there's emission between space carrying away the energy. But this is basically how the scheme works. The energy is removed by the electrostatic force of the trap. And the entropy is removed by the spontaneous decay of this vibrational state. It takes about 100 milliseconds. And if you take away a Kelvin of the cycle, we start with a few Kelvin of the molecules, kinetic energy of the molecules. And you just need a few cycles. So maybe after a few seconds or so, and we have tracking time for many seconds. Okay. So how do we implement it? Well, this is our molecule of choice. I have to introduce a few quantum numbers here. You probably all know this. This is our fluoromethane freon CH3F molecule. It has a carbon atom in the middle, and there are 3 hydrogens and a fluor here. The dipole moment is always belongs to the cavity axis. Nice symmetric form. The selection rules in this condition. please remember, just the transition to the first excited vibrational state have to come back to the vibrational ground state. And the selection rules on the angular momentum states is almost perfect. Delta K equals 0, delta J 0 or plus minus 1, and delta M equals 0 or plus minus 1. So what are K, what is J, what is M? Well, J is the total angular momentum of the molecule, it points in some direction. K is projection of this angular momentum J onto the symmetry axis of the molecule. That's how it's implied. And M is a projection of the angular momentum J on the direction of the electrostatic angular. This is how it's defined. And then these are the selection rules. They are pretty straight. There's nothing like a concordant factor that needs to be considered. There's no economic addition involved in this system. So why do we say, well, it's a simple symmetric top molecule, it has very good selection rules. I already said this. It has a strong dipole moment of almost 2 pi, so it allows for good electric trapping. It has very large rotational constants because the rotation around this axis is just the hydrogen. The moment of insertion is pretty small for the hydrogen, so it's rotating pretty fast. And the energy levels, J energy levels, angular momentum energy levels are separated by a large amount. So only a few states are populated when you start this molecule in room temperature. Then there is something else. We detect these molecules typically by mass spectrometry. And this molecule has a mass of 34. And as a mass 34, there's a low background at that mass. We have very sensitive detection or almost background to detection of molecules in our experiment. So good for mass spectrometry detection. And then it has a symmetric CH stretch mode at about 3000 wave number, which is 3.3 micrometer. So this is the optical transition is wavelength 3.3 micrometer. It's a parallel transition at a good wavelength. Good lasers are available at this wavelength. So technologically, it is kind of convenient to work with this model. And that's why we picked it. So here's how it works. So this is a vibrational excited state. Stretch mode indicated here. And this is a vibrational ground state. So nothing is vibrating. This here, and this is the trap. Outlined before. This is the trap in the excited state. This is the trap in the ground state. So we're talking here about the J equals 3 manifold. We pick J equals 3 states, which are populated. And significantly populated in this molecule. So the vibrational ground state B equals 0, J equals 3, and K equals -3. And the trappable states is M equals 3, M equals 2, and the M equals 1. But M equals 1 has just a small energy level shift, small stark shift. So it's not really guided very well. It's not really trapped very well. We have to avoid populating these states. So I'm just leaving it out for the purpose of making this scheme a little bit more simpler. I'll tell you on the next slide that it's a little bit more difficult than this. But let's assume it's like this. So now we have the molecule in the vibrational ground state coming out of our room temperature reservoir. There's nothing up here. And it's just trapped in this field. And we drive this radio frequency. Very much what I indicated before. So let's see how a molecule starts. So it starts here, it goes up. The radio frequency transfers it with some probability into the M equals 2 state, and it comes back. And now we have this infrared transition, the excitation at 2 points, about 3000 wave number or so, the infrared transition to the first excited vibration state. Selection rule J equals 3, K equals -3. We can select them. Please remember our trap has flat bottom. Homogeneous electric fields. So we can nicely address the individual energy levels that are separated with the energy or hidden space and wavelength space. Because of the homogeneous. So we excite this state and then it decays back, spontaneously decay back to the ground state. So this is a really good process that we are talking about. We are accumulating in the sense that we are driving delta M equals +1 transition. So we are driving M equals 2 into M equals 3, which even has a higher structure. So it's more trappable, more easier to trap. Because the M quantum number determines on how deep the trap for the molecules is. So it's N times The star shift is M times K. So when you increase M, the star shift increases, which means the trap becomes deeper. So we can actually accumulate. So this is key. I tell you one. Okay, the situation is not as simple as this because there is, for example, in the vibrational ground state, there's a J equal 4, K equal minus 3. So delta, please remember, delta K is equal to 0. J equal minus 3. So it cannot decay into a J equal 2 state, for example. Because J equal 2 state cannot have a projection on the symmetry axis of the molecule with K equal 3. But it can decay into J equal 4 state. So there is a J equal 4 state. So there is spontaneous decay, for example, into this J equal, into the J equal 4 state. But the nice thing is the physical cooling scheme, the radio frequency here is the same. So we can also cycle here. And then, but we have to bring the molecule back, and we bring it back with a microwave source. Because the spontaneous decay of these rotational scales, J equal 4 to J equal 3, would take forever. It's a rotational decay. It's slower than vibrational decay. So we find then microwave radiation, in this case around 200 gigawatts or so, and bring this state back to the ground state. Okay, you got it? Okay. So the scheme is a little bit complex, but it is not so complex that we cannot implement it because it basically needs an infrared laser, and it needs a microwave source, and it needs a radio frequency source. Radio frequency sources are easy to build. I mean, everyone can build them by yourself, basically. The microwave you can buy, 200 gigawatts. Hey, it's a little bit high frequency, but the frequency multiplying case you can buy from many companies. And the molecules, of course, are very sensitive to microwave radiation because it's large light components. So you don't need much power, honestly, for the microwave. Nano ones, even room temperature almost. Like water radiation at room temperature almost. Anyway, so in practice it looks a little bit more complicated. So as I said before, so this was the ground state, the vibrational J equals 3 ground state. This is a J equal 4 in the vibrational ground state, and this was the excited state. So there are more decay levels. So we have to actually apply more microwaves to deplete these states where the molecules get decayed into around these 204 gigahertz. So actually what we do is not one frequency of the microwave, but it's 3 frequencies. We just switch them. So basically, it's not a sleep in the microwave, but it's addressing this condition and this condition and this condition very rapidly one after the other. And then drive the molecules back into this state. And then there are some leaky channels, a little bit of a leaky channels, but the Clapeyron coefficients from let's say this state, for example, or that state, for example, into a lower M state is just very small and neglected. Well, what does it mean neglected? It would cool to norm the molecules would escape, and it would show as a loss mechanism. But the loss channel is very much. So basically, we can drive the full cycles in this physical effects and the full cycle of the conditions. The loss channel we can neglect because it kept going and that was okay, that's the key. Okay. So now how does it work? So we start with the reservoir here. In this case, it's a 120 Kelvin diffusive source containing our molecules to begin with. Please remember, we have this guide. We bring the guide as close as possible to the molecular source. We have this band. Only the slow ones make it around the band. The fast ones disappear, but they go straight and disappear at the pump. And then we have differential pumping here, and then maybe another differential pumping, and then this step region here with our entrance guide, and this is the exit guide, and this is our mass spectrometer for detection, which is also separated by a differential pumping scheme. So that's basically how it looks like. Our electric trap here, trapping potential of 1 Kelvin, trapping times of the order of 30 seconds or so. we shine in an infrared laser here, this laser that I outlined before, to already during the loading process drive delta M plus one transition in this way, so to say, bring molecules from a not so well trapped state into a better trapped state because the start limit is larger. So this is how it looks like. The molecules are coming, they're flying into this trap, they're moving around like crazy, and they don't find basically the exit hole. I mean, some of them come out at some point, there's a steady state reached after some time, sometimes after 30 seconds or so. Molecules coming in, molecules coming out, but because of this pumping laser here, this delta and the one transition pumping laser, the molecules that come out are in different states, or partly in different states, and the molecules that go in. So that's how you can imagine how the filling of the trap works. And then we close the entrance hole by switching the voltages. One can almost close the guide here, one can almost close the guide there. Then the molecules are trapped for these 30 seconds. And then we do cooling during this time. So we have the infrared laser, very much like I pointed out here. We have the microwave, we have the radio frequency, we scan it for the cooling. Implement the protocol as outlined before. So that works pretty well. And this result. And then at some point we open the trap. We switch this one to guidance, and then the molecule just come out, and we do time of flight spectroscopy or time of flight measurement. We see how rapidly molecule is coming out. From the time of flight, we can determine the velocity. So this is the time of flight signal. Time after opening the trap. And this is how many molecules come out in some normalized units. This is for the uncooled molecules, so they come out after 50 milliseconds, basically, because they need some time to travel. I can't remember exactly how far they travel, 30 centimeters or something. That comes next slide. So it takes some time, and then the molecules come out and reach basically a steady state after 150 milliseconds. This is the time of flight signal. When we cool them, so the cool is the blue one. When we cool them, it takes much longer for the molecules to arrive, something like 150 or maybe 200 milliseconds, and then they slowly turn on and reach a steady state. Of course, that not even reach a steady state. At some point, the trap empties, and then at a later time, it just decays. Because the reservoir is empty. So knowing the time of flight, we can determine the velocity distribution. And this is the velocity distribution of the cooled and the uncooled molecules, uncooled as a reference. So no cooling at all, and we choose from this kind of signal, we deduce the velocity distribution like this one. It's around 10 meters per second, and it has a width of plus minus 5 meters per second. This corresponds to a temperature of 790 millikelvin. This is our cooling. This here is the velocity distribution after cooling. It's peaked around 2.7 meters per second. And that corresponds to a temperature of 29 millikelvin. So we decrease the temperature by a factor of 10 or slightly more. And the velocity is from 10 meters per second to 2 something meters per second. And please look, I mean, the region where the molecules now go up was completely void initially. There were no molecules coming out at these velocities. And now they come out at velocities which are much smaller. So we are not post-selecting. We are not just so to say looking into this region here and blowing it up. No, we are really generating molecules in this region. And this is the size of this effect. You can it's not separated normalized. The area under this curve is how many molecules we have after cooling, and the area of this is how many molecules we have before cooling. So you can see the area is a little bit larger than this one. So we lose some molecules, but still we end up with about 100,000 molecules. It's a typical number. How do we know it's 100,000 molecules? Well, we count them with our mass spectrometer. We calibrate the mass spectrometer, and from that we know that it's about 100,000 molecules in this particular experiment. So that looks good. Here's the temperature as a function of the final radio frequency cooling. You remember we sweep it down. So we started at frequencies of around or more than a gigahertz, 1600 megahertz or so. And we plot the temperature and we plot the phase space density or this plot as a function of this radio frequency. This is the increase in phase space density, and this is the decrease in temperature. Okay, so we start up here with 400 millikelvin or so, and then it goes down all the way to, I don't know, 20 millikelvin or so here. And the phase space density we start, well, this is not phase space density of 1, sorry, it's increased phase space density. Right? We start with a very low phase space density, because everything comes from a certain source. But we normalize this to 1, and then we plot the increase in the phase space density, and it goes up by a factor of 20, 30. So it's not a gigantic increase in phase space density for this experiment, but still, it's a significant cooling effect. The temperature goes down, phase space density will go up. This is what we want. Okay, this is maybe also showing the molecule effect lifetime. So this is the lifetime effect in seconds as a function of this final radio frequency cooling. We start with something like 10-second lifetime. And please remember, as molecules get slow, they follow an erratic electric field in the vicinity of these plugged holes. They're not completely plugged, but when the molecules are fast, they can still make a transition from the low field seeking state to a high field seeking state. But when the molecules get colder, they can better follow the trajectory. That means in the end, the lifetime increases. So in this case, it increases from 10 seconds to something like 25 or 30 seconds. Half a minute. So that works very well. Well, the temperatures were not the lowest one we were hoping for. It's still in the millikelvin regime, so we want to be lower. We discovered that, of course, it's what we do at the beginning of this. The very first transition rate was kind of small, about 100 milliseconds. We switched the molecule out of formaldehyde. Because the main advantage of this molecule, the angular momentum quantum numbers are similar, but the main advantage is that it has a 5 times faster vibration in decay rate. So instead of 100 milliseconds or so, it's 20 milliseconds. So everything is faster. Please see that the lifetime was not so incredibly large. It was in the lifetime of the track, it was maybe 10 seconds or so. So cooling is comparable to that time, this trapping time, and to have a 5 times faster vibration decay rate, you would have. And this is why we switched to formaldehyde. And now we measure the temperature, just to make sure that we are not, so to say, measuring something which is maybe a crazy. We switched our detection scheme to a radio frequency 9 scheme. So look, the molecules are populating different M states here. And this is the edge of the track, so they increase, and we take a radio frequency 9 like this one, and we probe the number of molecules in the state here as a function of energy, how much they can climb the potential here. But driving a radio frequency transition with stronger electric fields, but driving them into an untrapped state. And then sweeping this down, and this way we can lead the trap of the molecules. And by plotting this depletion as a function of the radio frequency, we can determine the energy of the molecules. So that's what we do. And this is okay, yeah, we sweep it down very much like this. And then this is the result. So this is the integration molecule number as a function of the kinetic of their kinetic energy. And of course, at zero kinetic energy, there are 0 molecules. And the integrated thing increases here. And the mean kinetic energy, basically, if we take here the 0.5, is something like 400, actually 420 microkelvin. So with this molecule, we were able to cool the further down into the microkelvin, which is, if we take the language of atomic physics, which is the ultra cold machine. We can debate whether this is ultra cold, whether this molecular is a good one. but at least we are in the microkelvin, sub-millikelvin. And because it works faster for the formaldehyde, we have more molecules at the end left over. So it's about 300,000 functional codes track formaldehyde molecules. Fantastic. Well, that works pretty well. Any questions?
Could you summarize what's the difference between H2 CO and the CH3 fat? What these two are different?
What's the difference between this molecule and the other one?
I mean, like, what these two are different of the temperature? I think this configuration is almost similar.
Yeah, the configuration is almost similar, except for the fact that this molecule has a much shorter vibration life. So we can proceed faster. Proceeding faster means that we are not limited by the fat life. Our cooling scheme takes 10 seconds or so. If the fat lifetime is 10 seconds, we are losing molecule just because it's a life and it's a fat. If we could speed it up, we could cool faster, and that means in the end we could cool further down. So we have to slowly see the radio frequency. Every value can follow so the change in the energy distribution, and this goes faster for this molecule. Of course, there are plenty of differences between the CHF molecule and the formaldehyde molecule. CHF is an isometric box, it is not such an isometric box. So there are plenty of differences in practice. But fundamentally, I mean, there are not so many differences, except that the numbers are more big.
If the numbers are very similar and they're literally not so different, we initially started with 3 of them, but this one right there.
If you would have done otherwise, you would have asked the same question, but I don't know. I mean, in the end, they are trying to develop general message to cool any kind of molecule. So it's nice to see that it works for at least 2 different species. These are our favorite species. Why are these our favorite species? Well, I tried to explain for the clear molecule on one of the slides, and formaldehyde is it's a well, let me say, it's a well-studied molecule. Many things are known, frequencies, transition frequencies are known, rotating constants are pretty known. There are tons of research on please also remember in my introduction yesterday, I mentioned this collision, which are called chemistry collision, water and formaldehyde or Asian and formaldehyde. So maybe we would like to find that at some point. Now, I don't know. I mean, there are so many molecules around. I agree. Why just need 2? Symmetric tops are nice. So that's why we started with symmetric top. This is almost a symmetric top. I'd say maybe I should okay. There's one more thing I will not invest in so much. Formaldehyde can be completely investigated at a wavelength which is not too crazy. I mean, you might know this. The molecules do not have nice optical transitions, and they're typically deep in the ultraviolet. Formaldehyde is kind of nice because it has a transition. The first electronically excited state of around 300 for the 50 or 60 nanometers. So it's a moving transition, but it's also deep in the movie. So we did some spectroscopy, some optical spectroscopy on formaldehyde, just because this has a convenient kind of experimentally technologically convenient wavelengths. But I will not talk about the spectroscopy.
Probably not, I'm not sure if the temperature is correct at that. So before, but you said that you went roughly from 400 millikelvin to something like 30 millikelvin, right?
Yeah. Was the other one. And here it's
You went very low, I guess.
no,
So what kind of physics now you can explore, let's say in the case that you're roughly with 100 magnitude lower, right? Like 10 times loads.
that's tomorrow.
I understand it's super talented, but I would like
It's part of the answer tomorrow, but it's my talk is switched, I think, from so tomorrow. Maybe we can wait until tomorrow.
Okay. I wonder how the density inside the crowd.
Yeah, whether the collision comes tomorrow. At the moment, they're not enough. No, I mean, 300,000 is not enough. The volume of the track is about in cubics. Please remember, it was 4 centimeters long, 2 centimeters wide, and they use 2 or 3 millimeters high, which in the end gives something like a cubic centimeter. So this is 300,000 molecules in a cubic centimeter, which is the density of 375 per cubic centimeter, which is too small to speak of it. And these temperatures, course, they should are simply too small and trap lights and down the road. I will talk about that before. It's really many more. Fantastically many. I think this is kind of world records. So at least for this kind of volume. So don't underestimate this number. Don't get it out. And I will tell you a scheme of how to make these molecules larger. Orders of magnitude. That was the question. Okay. Anyway, so this summarizes a little bit the thing. The final temperature, as I said, in a few hundred microkelvin or so. We started at a few Kelvin room temperature, and then the temperature goes down by a factor of 26. The phase-based density from the initial at room temperature, when you to the final temperature goes up by something like 40 orders of magnitude. So yeah, it's still far away from the quantum gas. That's clear. That's very obvious. But it's 8 orders of magnitude.
Yes, I think we more turbulent. It's I think also more turbulent is like really, for example, 100 millikelvin or 1 kelvin, there is nothing quantum happening. Probably Twitter or what, but so this
I should never say that nothing happening. There's always something happening. Whether we discover
purely classical the behavior of the ensemble models.
we haven't discovered anything. And I am not aware of such a quantum that we could study and see phase-based densities and these. But I don't know. I mean, there might be collision molecules which one can already store. Not that easy. Okay, so I'm again too slow. I wanted to tell you also a little bit about the future. So the syllabus cooling cools down the external base of the molecule. Translation molecules are just moving at a smaller velocity. But the same scheme with the optical pumping and so on that I told you also increases, or sorry, decreases the internal temperature. It's a side effect of the pumping scheme of how we implement it. And very quickly, I don't want to go into too many details. This is the population, the calculated population of our states as a function of J. As a function of J on the number. Or I think this is again here. Or the it might come from one of these next slide. I think it's CH here. So this is what we expect, and this is the K equals 3. The blue one is the K equals 3 manifold. Please remember, we were working with the K equals 3 manifold. You can also choose to work in the K equals 2 manifold, but the K equals 2 manifold has less molecules. K equals 3 manifold has the largest spectrum of molecules indicated in the blue. Okay, so it starts at J equals 3, because K equals 3 requires at least, or it requires a J quantum number angular momentum of at least 3. So we start at 3, 4, 5, and then it goes up. So this is the total population in our ensemble lives in these blue indicated states. Which is already very nice. It's a significant fraction of our initial distribution. At room temperature. This is at room temperature. So there are 70% of our molecules in the J equals 3 and 4, K equals 3 manifold. Then 9% of the molecules, it's just the area here, and 9% in the J equals 5 and 6 manifold, K equals 3, and so on. And we would like to bring these internal rotational state to one state. So do internal cooling. Prepare even an internally pure sample of them. And so basically it goes with optical content. So this is J equals 3, J equals 4, J equals 5, and so on. We would like to bring the molecules from J equals 4 into 3, from J equals 5 to J equals 3. So how do we do this? Well, there's this excited vibrational state. We have our laser here. And the laser can, for example, deplete now the J equals 4 state. Why is the excited state? That we came back to the J equals 4, the J equals 3, the J equals 5, due to the selection rules, J equals 0 and plus minus 1. So it redistributes the population from 4. It empties the population with 4, let's say, and brings them into 3 and 5. But we want them in 3. We don't want them in 5. So we apply a radio frequency field or microwave field, in this case 300 gigahertz, and bring molecules from J equals 5 back into J equals 4. And the idea is to end up in J equals 3. So it's not even on the scale. In some sense, this is now a dark state because it's not addressed by a microwave, it's not addressed by a laser, it's just a dark state. Let's fall into that state. That's what we want. In fact, it is a little bit more complicated. So there are all these different end states, different because it's an electric field. So again, we need to switch our microwave fields, the frequency of the microwave is very rapidly between the individual positions here, but this can be done. Rapidly switching microwave synthesizer. And of course, there's more. There's 5, there's 6, there's a 7 stage. We do the same here. Let's say we also take a laser. We switch the laser from this wavelength to this wavelength. Basically, it's a rapid sweep of the laser. One laser, please remember. And then we empty basically this state, the J equals 6, J equals 7, very much along the same line, and pumps them into J equals 5, and J equals 5 goes to 4 and goes to 3. So everything ends up down here in an optical pumping cycle. That's the idea. And yes, we can do this. So we measure, let's say, the population in different states, J equals 3, 4, 5, 6, and separating 3, 4, and 5, and 6 as a function of time. And we do this protocol that I just tried to outline, and we see that state 5 and 6 is emptied. It takes about a second or so. Just remember, travel lifetime is maybe 10 seconds. So let's have on a time scale which is short compared to the traveling lifetime. So we deplete here, and they show up correspondingly in the 3 and 4 state as we were hoping for. And this is the sum of everything. So we're not losing molecules. So it stays the same. They've gone. They're not losing molecules. They're all pumped, so to say, internally from the rotational manifold. They're all pumped in the J state in this case. Actually, we pump them into a single M state as well. So let me just quickly outline. So the physical cooling happens between J equals 3, J equals 4. And this is the kind of signal that we get only during the automotive cooling. And now if we implement also this internal state cooling on the 5 and 6 manifold as described before, we are hoping for, let's say, 9% more signal. There was 17% here, 9%, which almost 50% compared to the 17% population in these states. Adding 9% more molecules from the total ensemble would give an increase of the signal by 50%. Okay, they're going from 32 to 70 plus now. Roughly an increase of 50%. That's what we see. With the rotational cooling implemented, we see an increase of 49%. So this is nice. We are not losing molecules, they're really shuttling them around in the internal state manifold. In fact, it's a little bit more difficult, as I already emphasized before. There's also stark splittings. The molecules need to be pumped here. Okay, this is getting too complicated. More than all the details. It requires a rapid switching of radio frequencies and microwave fields to address the different conditions here. And basically it was as expected, which is very nice. Anyway, so now let me switch gears. How much time do I have? So 5 to 10 minutes. Okay. So this is now a different cooling scheme, buffer gas cooling, invented and out. As far as I know. At least in this context. The idea is to bring in molecules into a region where there is a cold buffer gas. Let's say helium or neon. There are collisions at such a high density that the molecules which you bring in, let's say from this hole, molecules that you bring in collide with the helium and are cooled. What means cooling in this context? Well, kinetic energy or the velocity adjusts with the velocity of the helium. The helium is a very light molecule, so it moves fast, even at 4 Kelvin. So the molecules, when they collide with the helium, they will have, but they come out here, they will have almost the same speed as the helium. The main advantage that I see for the buffer gas cell is that the rotational degrees of freedom of the molecules coming in are cooled by collisions with the cryogenic buffer gas. It's the internal state cooling that really helps. I'm going to show you some numbers that really helps. It's not the motion internal state. Then the molecules, so to say, come out. At some point, they get cold. And again, we have these guides, and the guides have to colorful mass spectrum. Okay, so this is a standard technique which we have invented. Other people have done that, and other people are using this. So maybe other people are much more qualified to talk about all the stuff that's happening here. I just wanted to mention, so to say, we have this system in the lab. That's how it looks like. The cooling, this buffer gas takes place here. This is at the bottom of the cryogenic refrigerator. These are where the molecules come in, and this is where the molecules come out. This is our guide. The colorful guide is goes to a mass spectrometer, which is outside the picture. So how does it work? And how can we characterize the source? We are interested in the internal state distribution. What is the internal temperature of the molecules? So actually what we do is we have a little gap here of 1 or 2 centimeters in length, a little gap between the guides. There's one guide coming in, there's one guide going out, and there's a gap. Molecules fly out of the gap, so out of the guide into the gap. They fly into the other. That's what it works surprisingly well. I was really shocked by how good it works. How many molecules we can actually bring from one guide to the other one. Also, there's an unguided region of 1 or 2 centimeters in length. So why do we have this? Well, we apply a plate capacitor here in electric fields, and then we drive low heat seeking molecules into high heat seeking molecules and probe the internal state distribution. And the internal state distribution then shows up as a depletion signal in the mass spectrometer. Okay, we can address certain radio frequencies and it's a certain electric field. 5 molecules from one low heat seeking state into a high heat seeking state, and see how much the signal is. And then we probe different states. And from that we can determine the state distribution, and from that we can determine the temperature. So what is internal temperature? So this is the manifold here for CH3F. This is the J and K 2 and 1, 1 and 1. So this is the internal state, let's say. We drive transitions. And this is how as a function of frequency, the colorful mass spectrometer behaves. Okay, so there's a flat line normalized to 1 here, and then there are these depletion signals. We can attribute all these depletion signals to certain states. This is the J equal 1, K equal 1 states, J equal 2, K equal, and so on. And now we start the cooling. This one for low buffer gas densities. Let's say 0.4 times 10^15 per cubic centimeter, going up to 1, 2, 3, and so on. And what you can see is that the higher line states here, for example, the 4 state has a higher energy that really quickly goes away. And this state is the 1-1, and this state, the 2-1 state, basically survive. So by looking at how the higher line state gets depleted as a function of buffer gas density, we can say the temperature decreases. Internal state temperature decreases. For this, we can determine the temperature. So this is with neon as a buffer gas at 18 Kelvin. This is a state, K and K equal 1-1, 2-1, 3-1, as a function of the density of the neon, the density of the buffer gas. For small densities, we have a distribution in different states. For higher densities, we have 92 or 93% of all the molecules in the K-1 K. Almost pure sample. Almost a pure sample. And so we can systematically study, so to say, the internal temperature. So this is, for example, plotting the temperature, the rotational temperature, as a function of the neon density. We start at 5 Kelvin for a set temperature of 18 Kelvin. So we have 5 Kelvin internal temperature. How can that be? It's colder than the buffer gas. Where there's cooling at the exit, always is a supersonic expansion. And it goes down from 5 Kelvin to 3 Kelvin to something like 2 Kelvin. Okay. The internal temperature of the molecule is cold, 2 Kelvin. Cooling by hydrodynamic expansion. So what is hydrodynamic expansion? Well, it's not a random walk anymore, but it's trained in the gas molecules coming out. And the reason is why we have to increase the density actually. Then if you cool more and more, I mean, please remember, we want to have as many molecules as possible. We're sending in many molecules into the sample, but helium doesn't have a high cooling capacity. Specific helium is extremely small. Extremely small. So we have to increase the density of the molecule. So the density of the atom. But the density of the atom means that there are plenty of collisions of the molecule with the cryogenic buffer gas, even at the exit. And that makes it super strong. And then cools again. Cools to temperatures which are lower than the temperature. So the disadvantage of that is that the velocity distribution of the molecules coming out is peaked at, let's say, around 200 meters per second. They're very, very fast. Compared to an effusive beam, no buffer gas. Effusive beam would show a velocity distribution maybe like this one. But this has no slow molecules. So the molecules that come out of the buffer gas cannot be trapped in the they can drive, but they cannot be trapped in the electrostatic form. They're just too fast, 1 meter per second. And they're absolutely no slow ones. So the nasty, I would say, is cryogenic buffer gas was completely useless if you want to trap the molecules coming out of this electrostatic beam. They're too fast. They're simply too fast. They're internally cold, it's beautiful. The velocity distribution is kind of narrow, which is nice. They're just too fast. They're cold. 2 Kelvin. Addressing one of the questions from yesterday. The velocity distribution is kind of narrow, but they're just too fast in the lab. So we have to come up with a deceleration. We have to decelerate. And I think now if I have probably only 5 minutes left, so maybe 0 minutes left. I come to our deceleration.
A minute or two. You would use the transfer something.
I can transfer it to more. Depends on what you want.
My question is, in power group, I think they have a second stage cell to significantly reduce the boosting effect caused by helium or buffer gas.
Okay. I don't want to go into detail, but this is not, I guess. So, there can be a second stage, and we try to implement a second stage. It doesn't have much. That's our opinion. That's what we found. Doesn't have much. It has maybe a little bit, but it doesn't have too much. This is much better. So just a little bit of advertising. I can explain to you the rest of it tomorrow, maybe. Just as advertising. So you can think about it. We were wondering, how can you decelerate in a continuous way? How can you decelerate on continuously. I mean, please remember, smart decelerator, for example, is pulse. We don't want to have a pulse torch because the overall flux is very, very small. It's a beauty cycle. We have a continuous sort of molecules coming out of the bubble gas. We want to have a continuous deceleration. So the easiest thing to do is make artificial gravity or go into gravity. All the molecules up without material. But for 200 meters per second molecules, they climb thousands of meters. Not doable. Even if you write a hard proposal, you have a falling tower, an inverse falling tower, let's say, going up millions and so on for us. Not doable. Okay, all is not doable. So my thing was it's reverse sprinkler. It's in a completely different context, but somehow it triggers. So to say, my thinking, the way in which I will outline my next slide, and then I will stop. What is the reverse sprinkler? It's a famous example from 1883, Ernst Mach. He wrote a book on mechanics, the development of mechanics in a historical, critical description and so on. You all know what a garbage sprinkler is. Huh? It's basically this piece of thing. You put water into it, and then it starts rotating, and the water comes. And all of you, I guess, know exactly how it works, or how it's supposed to work. What? I mean, the water comes, I mean, there's this bend here. The water comes out with some angular momentum with respect to the axis, and because of angular momentum conservation, the angular momentum that carries away by the water must be compensated by this rotation. Very simple effect. You learn about it in school, even in kindergarten. It's fun for the kids, it's rotating thing. We know about it. Nice. The one thing about the puts the whole thing in a pool of water. And now it starts trying to get the water out through these arms, out through into some pond. Will this rotate? The other way. Will this rotate? The other way around? Yeah, of course, the other way around. Will it rotate? So Ernst Mach asked this question, and he couldn't answer it. It only means something. Ernst Mach was a great physicist. One of the other persons who thought about it was Feynman in 1940. Feynman couldn't come to a solution. Feynman, once in his life, made an experiment. Exactly this one. And went into some lab, built this thing, put it into the water, was trying to do this one. What happened is the water placement was completely destroyed. The lab was flooded with water, which Feynman was not allowed to go into the lab anymore. There are some historical notes in one of the books. So many people thought about it, and actually you can find YouTube videos of this thing. YouTube videos. And in some of the YouTube videos you see it rotating. How much of YouTube videos you don't see it rotating? If you do statistics over the YouTube video, they will conclude that the rotating here and rotating here. Nothing in between. What does that mean? So the answer to the question is maybe still open. There's, by the way, a very nice PhD by Jenkins 2006, who we consider this a thinking solution. Okay, so I don't want to talk about this. This triggered me a little bit to what I call a reverse centrifuge. Centrifuge accelerator for molecules. So think of an electric guide, a colorful guide, which goes on a disk, on a rotating disk, actually goes like a spiral into the center. Just that what I want to say. It goes through the rotating disk on the spiral. Now there's a molecule. The molecule, so to say, in the lab, and there's this rotating spirally shaped photovoltaic. So there's a molecule coming, and we let it jump on the disk. By a mechanism that I will explain to you. It jumps on the disk. So now it sits on the disk and it's rotating. What that means is the reference frame of the rotating disk, the velocity of the molecule has increased. It was rapidly moving in the left frame, let's say it's 200 meters per second, and it jumps on the disk, and let's assume it's moving at 100 meters per second at this position. Then in the left frame of this rotating thing, the molecule is moving only with 100 meters per second. So the velocity has increased by a factor of 2, which is already something. So the kinetic energy has already increased by a factor of 4. Just by putting the molecule on the disk. And then let it guide into the center along the spiral. This thing is rotating along the spiral to the center. It has to climb the centrifugal barrier by doing this, and it comes to rest at the center. Just climbing the centrifugal barrier. Then if you leave it there, it will roll back from the centrifugal barrier and nothing is gained. So the idea is to take it off on the axis. So the molecule goes away from this rotating disk, and it goes away on axis. That means it doesn't gain kinetic energy on axis. So that allows us to continuously decelerate past molecules, continuously operate. So they're continuously coming molecules, they're continuously picked up by the disk, they continuously expand. And how it works in practice, I guess I'll show you tomorrow. Thank you very much.
Yeah. Number of questions, you just respond, your moral assessment is set up. If you have questions, please come forward and ask everybody, and then of course we have all the time and after.
One can stand here.
Yeah.
One can stand there as well.
I think so. Yeah.
Oh, great. I'm afraid of this one. Oh, apparently no questions, so. They ask many questions.